The floating out and placement of this production platform in the North Sea is the first on-site physical evidence that a new field is to be developed. But the decision to develop the field was made a number of years earlier, before construction. And that decision, what we refer to as the development decision, was based on an interplay between economics and technology. Soon after exploratory wells are drilled on a prospective field, the analysis required for making the development decision is begun. Both reservoir and economic models are prepared using the specific data for this field, teams of industry specialists, and computers. The economic model is concerned with product prices, interest rates, capital and operating costs, taxes, and return on equity. The reservoir model, on the other hand, is concerned with the performance of the field under different well locations, flow rates, pressure response, EOR programs, and so forth. It is the integration of these two models that allows us to reach an optimal development strategy. Our concern in this module is the reservoir model, which is used to predict future reservoir performance. In order for these predictions to be realistic, the reservoir model should approximate as closely as possible the actual reservoir. This requires that all reservoir data be measured and recorded as accurately as possible, and then interpreted carefully, and finally used by the reservoir engineer to predict future performance. Let's first talk about measurement. Reservoir data come from many sources: geophysical surveys, wireline well logs, well testing, core analysis, and reservoir fluid analysis, often referred to as PVT, or pressure volume temperature analysis. The interpretation of these data leads to individual models: the geophysical model, the log model, well test model, and rock fluid model. Essentially what various specialists think the reservoir looks like. It is then the function of the reservoir engineer to incorporate these individual bodies of reservoir data into a cohesive whole, the reservoir model, and to then make accurate predictions about the future performance of the reservoir under different development strategies. A mistake could be very costly, and so care must be taken at each step of the process.
Hello and welcome to the PE 400 series of modules on sampling and well testing, where we shall devote our attention to three important parts of the reservoir model: well testing, core analysis, and reservoir fluid analysis. This module, PE 401, is the first in the series and is designed to introduce both the engineer and other industry personnel to well testing and measurement. To make things a little easier, we will avoid mathematical derivations at this point and leave them to subsequent modules in the series. Here you will learn how the reservoir pressure responds to flow, what and why various well tests are run, how we interpret the results, and how we measure and record pressure and flow during a test. Let's begin then by learning how the various well tests are conducted and what happens in the reservoir during a test.
A well test in its simplest form consists of producing a well at a controlled flow rate for a period of time and measuring the pressure response at the well itself or at some nearby observation well. The resulting pressure response, which depends on the rock and fluid properties beyond the well bore, is then used to describe the unknown reservoir system.
Thus, by measuring pressures only at one of the wells, we are able to quantify reservoir properties away from the wellbore, say between these two wells. Let's describe graphically what occurs during a well test. Here is a section of the Grand Canyon showing a number of upper sedimentary layers. Let us assume that this zone, which is about 50 meters thick, has hydrocarbon potential, that we have drilled a well through it and have verified the presence of hydrocarbons.
To simplify matters at this stage, we are going to make this a somewhat idealized reservoir. We will assume that the zones immediately above and below the hydrocarbon zone are impermeable, and that the reservoir is very large in radial extent. In essence, with an infinite outer reservoir boundary and a constant thickness. We will also assume that the reservoir has the same properties throughout and that these properties do not depend on direction. That is, the reservoir is homogeneous and isotropic. The well fully penetrates the zone and is perforated throughout the interval. No damage was done to the formation during completion. Further, if we open or close the well at the surface, the fluids in the formation respond immediately. This assumes that there is no compression or storage of fluid in the casing and tubing. A few more assumptions are listed in your manual.
Now what we want to do is conduct several different flow tests on the well and see how the pressure in the reservoir responds. To do this, we will need a pressure reference system. Let's say that we will measure pressure along a line through the center of the reservoir and record the pressure distribution along this line with a pressure versus radius diagram, as we see here. The well has not yet been opened to flow, and so the pressure at all points along the measuring line is the initial pressure P sub I.
Okay, now let's open the wellhead valve and allow the well to produce at a constant flow rate. This type of test is referred to as a drawdown test. Fluids begin to flow into the well, and a pressure transient moves outward, initially quite fast. But as the transient moves further out and more reservoir volume is contacted, the rate of movement becomes progressively slower. Wherever we see a pressure gradient, we know that fluid is flowing from a point of high pressure to a point of low pressure. The velocity of flow depends on the local pressure gradient, and so near the wellbore it is very high. Further outward, it is quite low. If we look down on the reservoir in plan view and record the distance over which a significant pressure disturbance has been propagated, we see that it moves out radially in circles of ever-increasing radii. We refer to this type of flow as radial flow, and to the radius of the leading edge as the radius of investigation.
Now notice this. If we run this test at a number of different production rates in our idealized reservoir, we reach an interesting conclusion. The rate of outward movement of the radius of investigation is the same at all flow rates.
This means, then, that you cannot investigate further into the reservoir, that is to a given radius, more quickly by testing at a higher production rate. The radius of investigation concept, then, provides a guide for well test design. Now let's see what happens if the properties of the reservoir rock or fluids are changed.
Let's take the test we just ran and freeze the pressure profile at an instant in time. Now, if we perform the same test on a system with a lower mobility, that is, a tighter formation with a lower permeability, or one containing a higher viscosity fluid, all other variables remaining unchanged, the pressure profile changes. It looks like this. Note that the pressure transient has not moved out as far into the formation, but that the pressure near the wellbore is lower. This means that more production comes from the region near the wellbore. For the same time period, the radius of investigation is smaller than in the previous example. Now, if we reverse ourselves, introduce a higher mobility, either by having a higher reservoir permeability or a lower viscosity fluid, we get this profile. Note that its pressure transient has moved out further into the reservoir and that the pressure has not dropped to as low a value near the wellbore. This means that production comes from a greater distance than in the other cases, and that the reservoir is investigated to a greater radius than the previous two examples. We can compare the relative positions of the radius of investigation in plan view. First, our base case, say for an intermediate viscosity crude, then that for the lower mobility, say a heavier oil, and finally that for the higher mobility, for example, a volatile oil.
There are three very important conclusions that can be drawn. First, the pressure near the wellbore will drop rapidly for a low mobility reservoir and slowly for a high mobility one. Second, if a well test is intended to investigate a certain distance into the reservoir, The required duration of the test will depend upon the relative values of permeability and fluid viscosity. And third, as we said before, the radius of investigation does not depend upon the selected production rate. The pressure transient will move outward to the same distance in the same period of time, whether the production rate is high or low.
Now let's see what changes occur if the reservoir volume is not infinite, but finite, owing to the presence of an enclosing no-flow boundary. Let's say that the limiting outer radius of the reservoir is at a radius r sub e. No flow can take place across this outer reservoir boundary, and all production must come from the inner region. If we open the well to flow again and watch the pressure transient, we see that the outer boundary does not affect its slope until the radius of investigation reaches r sub e. Then the pressure profile drops more quickly than it would for the infinite reservoir case, because all of the production must come from the finite reservoir volume. In a sense, an additional pressure transient is reflected backward toward the well that otherwise would have continued outward for an infinite reservoir. Soon after the pressure profile reaches the outer boundary and is reflected back to the well bore, we have the start of what we call pseudo-steady state or stabilized flow. Under these conditions, the rate of change of pressure with time at any radius is constant.
The drawdown test gives us a good way of estimating the properties and limits of the reservoir. However, in cases where it is difficult to maintain a constant production rate during a drawdown test, we might choose to conduct a build-up test.
In a pressure build-up test, we allow the well to produce at a fairly constant rate for a period of time, then shut it in and allow the pressure to build up again. We see here what the pressure transient looks like in the reservoir.
By recording pressure buildup during the test and using standard interpretation techniques, the properties of the formation may be estimated. This test is used frequently because of its simplicity. There are several extensions to the buildup test. For an injection rather than a production well, we might inject fluid at a constant rate into the well and then shut the well in and measure the pressure fall-off. These are referred to as injectivity and fall-off tests rather than drawdown and build-up tests. Their responses, though, are similar. Another well test is the so-called multiple rate test, where we flow the well at different rates and note the pressure responds.
The conventional back pressure test for a gas well is a classic multiple rate well test. As we see in this excerpt from PE 402, the well is flowed at 4 successive flow rates. Each flow rate is different and lasts until the pressure stabilizes. The flow periods are followed by an extended shut-in period. With this information, the engineer is able to predict the future deliverability of a gas well. The drill stem test, or DST, discussed in PE 404, is another form of multiple rate test. Now let's consider a totally different class of well test, one that is possible if more than one well is available. Here, for example, we have drilled an offset to our Grand Canyon well. If the second well is used as a pressure observation well, we may measure the pressure response in the observation well to changes in flow rates at the active well, and thereby understand the reservoir properties that exist between the wells. We refer to this type of test as an interference test, because flow from the active well interferes with the pressure in the observation well. There is a special type of interference test called a pulse test, which is conducted by changing the flow rate at the active well several times by alternating the flow and shut-in periods. This leads to a series of pressure pulses. The pressure distribution during a pulse test is shown here. Usually a number of pulses are introduced in a sequence. Here we see the pressure response measured at the observation well during the pulses. The shape and arrival time of the pulse in the observation well is used to estimate the properties of the reservoir between the two wells.
Of course, under actual conditions, we are able to record such pressure changes only where wells penetrate the formation. That is, either at the test well or the observation well.
By limiting our pressure measurement to the well bore, we can plot the production rate and pressure response at the wellbore versus time. Time, not radius, is now plotted on the horizontal axis. We note the original pressure, P sub I. We open the well to flow and see the pressure response for the drawdown test applied to the infinite acting reservoir. This is a classical wellbore pressure transient response. Note that the change in pressure, delta P, and elapsed flow time, delta T, may be recorded at any time. If the reservoir is finite rather than infinite in radial extent, then the early transient pressure response period will be the same until the outer reservoir boundary is felt at the wellbore. When the boundary effects are fully developed at the wellbore, the pressure will respond to pseudo-steady-state flow, which, as we mentioned earlier, is indicated by a constant change in pressure with time. In effect, the straight line we see here.
The straight line tells us that there is a bounded reservoir. We may use the value of its slope, along with equations in the manual, to calculate reservoir volume or areal extent. In so doing, we are able to estimate the effective outer limit of the reservoir. We see here how the pressure response of each type of reservoir is different. We shall see shortly how plots of delta P versus delta T are also different.
As we said earlier, it is often easier to perform a build-up test. We do this by allowing the well to be produced for a period of time at a reasonably constant flow rate. And then, at time t sub p, we shut it in. The wellbore pressure now begins to build up again. In time, it should go all the way back to P sub I for an infinite reservoir, or to some lesser average reservoir pressure. Call it P sub R bar for a finite reservoir. Let's summarize what we've learned so far. We have seen that the reservoir model is an important aspect of the development decision, and that well testing plays an important role in defining that model. Starting with an ideal reservoir, we have developed an understanding of the pressure response that occurs in the reservoir during the many well tests that are conducted. We have seen how they differ for infinite and finite reservoirs, and for differing reservoir properties. In our discussions, we have developed a list of the principal well tests: drawdown, build-up, injectivity, fall-off, multiple rate, interference, and finally the pulse test.
You should now have a pretty good understanding of each. Before going on to their interpretation, please pause the tape and work exercises 1, 2, and 3 in your manual. The flow conditions in an actual reservoir might differ substantially from the ideal reservoir of Unit 1. In this unit, then, we shall discuss the non-ideal conditions that we might encounter and learn how they affect flow characteristics. Interpretation will then be much easier.
Now we wish to define the conditions of a reservoir more systematically. We may divide it into 3 principal regions. Region 1 is the wellbore and near wellbore region. Mathematically, this is referred to as the inner boundary conditions of our reservoir. Region 2 is the reservoir description itself, which mathematically is referred to as the basic model. Finally, we have Region 3 at the outer extent of the reservoir, what we call the outer boundary conditions.
There are 3 inner boundary conditions within Region 1 that are commonly found in practice: wellbore storage, skin, and induced fractures. When a well about to undergo a drawdown test is opened at the surface, the flow rate at the surface versus time looks like this. The force driving the production to the surface is provided in large part by the decompression of fluids in the wellbore. The flow rate from the reservoir versus time looks like this. Showing the 2 flow rates simultaneously, we see the magnitude of delay in flow response at the formation. The delay is caused by what we call unloading, a form of wellbore storage. The delay in flow at the formation is also reflected by a delay in any pressure change in the formation. If we produce the well for a period of time and then shut the well in, as we would for a build-up test, we see that wellbore storage is also present for a build-up test. At the surface, the flow rate drops sharply to zero. The wellbore flow rate, though, drops more gradually to zero. The difference is caused by another wellbore storage effect, afterflow, caused by fluid compression in the wellbore. Note also that wellbore storage takes place early in the life of a well test.
The second inner boundary condition is skin. We also discuss this effect in PE 402 and PE 403. The skin factor is a quantitative measure of the damage or enhancement to the formation that exists in the immediate vicinity of the wellbore. A positive value for the skin factor indicates damage. A negative value, enhancement. Unless the wellbore damage is removed during the test, the skin effect is not transitory, but is present throughout the test period, and its effect depends on the flow rate.
The third near wellbore condition is known as induced fractures. A vertical fracture induced near the wellbore, as we see here in plan view, will result in a linear rather than a radial flow into the wellbore for a short period of time after the well is open to flow. In time, the ellipses will become circles, but the early linear flow patterns provide a characteristic pressure response, which we may measure and interpret.
In describing the conditions that may exist in Region 2, the reservoir itself, we have found it convenient to refer to the reservoir as either homogeneous or heterogeneous. The homogeneous acting reservoir is one that, with respect to flow, acts as though it has identical properties throughout, either because it is truly homogeneous or is so randomly heterogeneous that it acts as though it were homogeneous. Many reservoirs throughout the world fall into this classification.
The heterogeneous acting reservoirs have been the subject of many recent developments in well testing analysis. These reservoirs are divided into two types, double permeability and double porosity. A double porosity reservoir consists of two homogeneous porous media of distinct porosity and permeability characteristics which interact. An example of a dual porosity reservoir is the fissured or naturally fractured reservoir such as we see here, as it might actually exist, and in a more idealized representation. In this type of reservoir, a high permeability natural fracture system delivers fluids to the well, while low permeability matrix blocks bleed fluid into the fracture system. A second dual porosity system is the multi-layer system. In this two-layer system, only one layer acts as a source of fluids. The other layer delivers fluids to the wellbore. Both of these reservoir systems exhibit the same double porosity response to flow during well testing.
The double permeability heterogeneous reservoir is characterized by two distinct porous media, as in the case of a double porosity system, but in this case, each medium can produce into the wellbore. Now let's move on to conditions in Region 3, the outer reservoir boundary.
As we said earlier, a reservoir may be described as infinite or finite acting. The infinite acting reservoir is one that is very large and where the fluid communication is extensive compared to the drainage area of the well. In the finite acting reservoir, the reservoir volume communicating with a well is limited, as in the case of the limited reservoir that we discussed in Unit 1. Here, the reservoir outer boundary acts as a barrier to flow and is referred to as a no-flow boundary. A second type of finite-acting reservoir occurs where a constant pressure is maintained on the reservoir boundary, for example, where a large active aquifer is in communication with a smaller oil field. Another example is a producing well surrounded by a regular pattern of injection wells. This condition is referred to as a constant pressure outer boundary.
We have now completed the task of defining the various regions in our reservoir system. We understand that we describe or model a reservoir system by combining elements from each of the three regions. For example, We may have a wellbore reservoir system with wellbore storage and skin in a homogeneous reservoir of infinite extent, or one with wellbore storage and an induced fracture in a homogeneous reservoir of finite extent with a no-flow outer boundary. Of course, many other combinations are possible.
But you may well ask which of the possible descriptions best fits a given reservoir. A little further explanation is needed. By mathematically simulating the performance of many different reservoir systems, we have found that each of the reservoir model elements will exhibit a different pressure response during a well test, and that the differences can be observed in the pressure profiles recorded during the test. To express the pressure response graphically, we need to plot the recorded pressure versus time in some form.
Because pressures decrease during drawdown tests and increase during build-up tests, we generally plot the difference in pressure, delta P, observed during a test versus the elapsed test time, delta T. To avoid distortion of scale, we can plot these variables on a log-log scale. From Unit 1, we know that the earliest recorded pressure data during our well test reflects the wellbore reservoir system's response to wellbore storage. We refer to this test period as Period 1. Next in time will be the pressure response at the wellbore shortly after production begins from the reservoir. The pressure response information obtained during this period, Period 2, will depend upon the presence of induced fractures, skin, fissures, or multilayers. Next, after a period of transitional flow behavior, the pressure response will begin to exhibit the properties of infinite acting radial homogeneous flow. This constitutes Period 3, and the pressure response will continue if the reservoir is infinite acting, or will begin to change again for a finite acting reservoir during Period 4. The latter pressure response will occur once the pressure response to the outer boundary reaches the wellbore. Let's look more closely at the characteristics of each period.
In Period 1, the earliest condition observed, wellbore storage, exhibits its own characteristic pressure response shape. It yields a log-log straight line of unit slope at early time. This means that if the pressure data recorded during a well test has a unit slope log-log straight line passing through early time data, wellbore storage conditions exist. This is our first characteristic, or as it's often referred to, diagnostic plot.
Next, we look at the characteristics of induced fractures. The pressure response to induced fractures occurs during Period 2 and has two characteristic shapes, one for a high conductivity fracture, the other for a low conductivity fracture. A high conductivity fracture communicating with the wellbore yields a log-log straight line with half-unit slope, meaning that delta P is proportional to the square root of delta T. The diagnostic plot of a low conductivity induced fracture communicating with the wellbore will yield a log-log straight line with a quarter-unit slope, indicating that delta P is proportional to the fourth root of delta T. Note that the pressure response to an induced fracture during a well test will appear later in time than for wellbore storage. Thus, for example, the diagnostic plot may initially have a unit slope for wellbore storage and then be followed by a transition to half-unit slope for a high conductivity fracture.
As Period 3 begins, the pressure response begins to reflect infinite acting radial flow. This means that the leading edge of the pressure wave now moves outward radially, as if the reservoir were infinite in extent. In time, this pattern may be interrupted by a finite outer reservoir boundary, but for at least some of the time, the pressure responds as if the reservoir were infinite. During the infinite acting radial flow of Period 3, a plot of delta P, not log delta P, is a linear function of log delta T. In effect, we have a semi-log straight line. Plotting the same data on the diagnostic plot of log delta P versus log delta T yields a curve like this one for a homogeneous reservoir.
And when does radial homogeneous flow begin?
That's an important question. We have found that it depends on the near wellbore conditions. We won't discuss it here, but you will find more detailed comments in your manual.
The last pressure data to be recorded during our well test during period 4 will give us information about the outer boundary conditions of the reservoir. If the reservoir is infinite acting, radial flow will continue. But if it is finite, with either no flow or constant pressure conditions, infinite acting radial flow conditions will come to an end when the effect of the outer boundary is felt at the wellbore.
For a no-flow boundary, as we see in this diagnostic plot, delta P begins to increase with time and approaches a unit slope straight line. If we plot delta P versus delta T, we see that the curve changes and becomes asymptotic to a straight line at later times. The slope depends on the reservoir size and flow rate.
On the other hand, for a constant pressure outer boundary condition, a stabilization in pressure occurs. This means that delta P will approach a constant value with time. Now let's summarize. We realize that the log-log behavior of a complete model reflects the superposition of the log-log behavior of each individual component of the model. Here, for example, we see the characteristic curve for a well with wellbore storage in a homogeneous radial system with a no-flow finite reservoir boundary. And here is one where a low conductivity induced fracture has been added to the system. And finally, here we see one with wellbore storage producing from a heterogeneous reservoir of infinite extent.
Seems to me like all we have to do is plot the pressure recorded during a well test in proper form and then identify the pattern. Is that right?
Just about. But that comes in the next unit. Let's take a moment here to summarize. In this unit, we have taken a step beyond the ideal reservoir model we talked about in Unit 1 to model more closely the actual conditions that exist in a reservoir.
We saw that the reservoir may be divided into 3 major regions, which are defined according to their physical or mathematical description.
After we defined these regions, we then specified the conditions in each that would affect the pressure response during 4 different time periods of a well test.
We then introduced the diagnostic and specialized plots of well test data and used them to characterize and distinguish the various elements of our reservoir model. We now know that test data may be plotted and the resulting pattern analyzed in order to define the characteristics of the reservoir.
We are now ready for the specific details of interpretation, which we shall discuss in the next unit. For now, please take a few minutes to work exercises 4, 5, and 6 in your manual. By convention, the quantitative analysis of well test data has been divided into 2 broad categories: conventional well test interpretation methods and modern well test interpretation methods. The conventional methods were introduced and developed in the 50s and 60s and only make use of test data recorded in the latter part of a well test, that is, during what we have been calling periods 3 and 4. The modern methods, developed in the 70s and 80s, make use of all of the data recorded during a well test from periods 1 through 4.
As we discuss each in turn, we shall use the data of a specific test, a build-up test, shown here as a log-log plot of delta P versus delta T. Additional data about the test are in your manual. The conventional methods are based upon the original Horner and Miller pressure buildup analysis. The reservoir system model is quite ideal. It assumes a homogeneous reservoir structure with skin and may be of infinite or finite lateral extent. Wellbore storage may be present, but it is not analyzed. A few other conditions discussed in Unit 2 are also not analyzed. Horner solved the equations for his reservoir system and developed a graphical method of quantifying the results of build-up tests. For oil wells, a plot of the bottom hole pressure, P sub WS, versus T sub P plus delta T over delta T during a build-up test should yield a straight line on semi-log paper. Note that T sub P is equal to the average production time prior to shut-in, and delta T is the time since the well was shut in for the build-up test. For gas wells, the vertical axis is slightly different. At early time after shut-in, a condition equivalent to a large value on the horizontal axis, we see that a straight line normally does not exist. This deviation is caused by well-bore and near well-bore conditions. In time, a straight line may be drawn through the data, and it is this straight line that is used to define the reservoir system.
For example, if we have an infinite reservoir system, we may extrapolate the straight line to a horizontal axis value equal to 1 to give us the initial reservoir pressure, in this case 3,878 psi.
We may measure the slope of the straight line and with it calculate the formation transmissibility and then estimate the flow capacity and effective permeability. We see the values for the example well here. With this information, we are able to estimate the potential flow rate of the well under different flowing conditions.
We may also estimate the skin effect by finding the value of pressure along the straight line when the well has been shut in for 1 hour. We see the extrapolation here. The 1 hour shut-in pressure is equal to 3,797 psi. Using this value and the appropriate equation, which appears in your manual, the skin factor is calculated to be 7.4, a positive value. From our discussion in Unit 2, we realize that a positive value means that damage exists around this wellbore, and it is quite large.
Knowing the skin factor and other calculated values, we may estimate the flow efficiency, that is, the ratio of the well's pressure drawdown with skin to that without skin. We find the flow efficiency to be equal to 0.467. This, in turn, means that the actual flow rate, just prior to the test, for this well, about 174 barrels per day, could be increased to about 373 barrels per day if the skin were to be removed, for example, by stimulation.
The productivity index, or PI, is equal to the well's actual flow rate divided by the drawdown. That is, the average reservoir pressure, P sub R bar, in this case equal to P sub I, minus the flowing wellbore pressure, P sub WF, before the well is shut in. For our test well, the PI is calculated to be 0.22 barrels per day per PSI. The PI indicates the rates to be expected at various drawdowns. The flow rate will increase if the drawdown can be increased.
Finally, by using the test data and the calculated results, we may estimate the radius of investigation, the radius that the pressure transient, which we introduced by shutting in the well, penetrated into the formation. Our calculations show it to be about 256 feet, or 78 meters. If we had wanted to investigate further into the formation, we would have needed to test for a longer period of time.
We see that conventional methods of interpretation provide us with a substantial amount of information about our reservoir system. Modern methods, however, go a little further. They allow us to extend our analysis by considering early time data and both homogeneous and heterogeneous reservoir systems. We shall see that both methods are usually used for comparison purposes and that the engineer should be familiar with each.
By now we understand that the objective of a well test interpretation is to identify the reservoir system, knowing only input and output signals, and possibly some other reservoir characteristics. The input signal I is the controlled flow rate, and the measured output, O, is the change in reservoir pressure. Interpretation relies on models of the system, S, whose characteristics are assumed to represent the characteristics of the actual reservoir. This is usually referred to as the inverse problem, and its solution is usually not unique.
In the modern methods of well test interpretation, many investigators have considered the many different combinations of the elements of the reservoir system we discussed in Unit 2 as the S in the inverse problem, applied the test conditions for input I, and developed various forms of output, O. The output for each different investigated system is typically given in graphical form.
In order to develop a method of evaluating the data from these simulated well tests that would be independent of the nature of the specific well or reservoir being tested, the industry developed a series of what are called type curves to represent many different reservoir conditions. A few minutes reading about them in your manual, You should be using them with ease.
Type curves are generally log-log plots, not of delta P versus delta T, as we discussed earlier, but of dimensionless pressure, P sub D, versus dimensionless time, T sub D. Since a dimensionless term has no units, it can be used for many different reservoir systems, rather than for just a few. Investigators have proposed various forms for the dimensionless pressure and time terms. One such set is given here. Note that P sub D is written in terms of delta P and T sub D is written in terms of delta T. Each term, however, is dimensionless and includes other variables that are specific to the wellbore and reservoir system being tested. Type curves are available for many different reservoir models. For example, one such set has been prepared for a wellbore reservoir system with wellbore storage, skin, and a reservoir exhibiting infinite-acting homogeneous flow behavior. For this type curve, the dimensionless time axis has a term C sub SD added. C sub SD is the dimensionless wellbore storage constant, and C sub S the wellbore storage constant. Note that the presence of wellbore storage is exhibited on this plot by a straight line of unit slope at early time. Each different curve represents a different level of skin. Curves above the middle of the chart represent damaged wells, while those below represent acidized and hydraulically fractured wells. The region in between represents a non-damaged well. The start of infinite-acting radial flow, which occurs at initiation of the straight line on the Horner plot, indicates the end of wellbore storage, and is shown here as two separate curves intersecting the type curves.
Type curves for many other reservoir models have been published in the literature, and a selection of them is given in Appendix B in your manual.
To use the type curves, we begin with the log-log plot of delta P versus delta T for the data from the well test we looked at earlier when we discussed the conventional interpretation methods. We analyze the test data pattern to identify the dominating flow regimes, remembering the characteristic shapes of the various reservoir elements discussed in Unit 2.
Now we need to select the appropriate type curve. In this case, because of the unit slope at early time and near straight line at later time, we have identified a model with wellbore storage, skin, and radial homogeneous flow. We then select a type curve that includes these reservoir system components.
The next step is to draw a Horner plot. As we saw earlier, this will give us values of K sub OH, P sub I, and S, which we can then compare with the values generated by the type curve analysis.
We then superimpose the diagnostic plot of our test data onto the type curve to obtain a match. Initially, this is done by sliding the diagnostic plot over the type curve, aligning the straight line at early time, and selecting the best possible match curve. Obtaining the match curve is often difficult, so we usually seek an estimated match point using Horner plot data. This provides an initial vertical match. The horizontal match is found by shifting the characteristic plot horizontally until the early time straight lines are aligned. In doing so, the final value for the pressure match point may be modified slightly. The final match point for our example data gives P sub D of 1.79, matching with delta P of 100, and delta T of 1.0, matching with a ratio T sub D over C sub SD of 14.8. Details are in your manual.
Once a unique match point has been obtained, we may rearrange the dimensionless variables to give values of K sub OH equal to 1,165 millidarcy feet, and a skin factor of 7.7, and a wellbore storage constant equal to 0.0093 barrels per psi. Comparing the results obtained using the Horner plot, specifically the values of K sub OH and S, we see that the correspondence is quite close, and thus gives us confidence in our description of the reservoir flow system. In this example, the flow behavior exhibited radial homogeneous flow, essentially the basic assumption of a Horner plot, and so the results should be similar.
There is considerably more data and many more reservoir systems that we may investigate with type curves. but that comes in later modules. Let's now summarize what we have learned in this unit.
There are two major methods of interpreting well tests. The conventional methods rely on methods such as the Horner graphical method for interpreting well data.
The modern methods are based on the solution of the inverse problem and rely on the matching of test data to type curves, which have been prepared for a number of different reservoir systems. The interpretation of well tests using type curves is a graphical analysis procedure which uses pattern recognition as its central concept.
More information may be obtained using modern methods, but neither method is used in isolation, since it is often difficult to obtain unique solutions. Thus, a blend of approaches is necessary for consistent interpretation. Before going on to the last unit, please work exercises 7 and 8 in your manual. We now turn our attention to some of the practical aspects of well testing, specifically the control of flow rate, measurement of pressure, the required surface test equipment, and finally a few aspects of test design.
The control of flow rate during a well test is usually achieved at the surface through the use of chokes. In this drill stem test system, for example, 2 chokes are located in parallel in the floor manifold. One is an adjustable choke, the other a positive one. Flow is directed through the adjustable choke initially to determine the suitable choke size for the desired flow rate. Then a proper size insert is placed within the positive choke to maintain the constant rate. Flow is then directed through the positive choke. Once the flow rate is controlled, we turn our attention to measuring pressures. There are 2 types of recording instruments used to record pressures during a well test: mechanical and electronic gauges. The pressure element of a mechanical gauge is normally of the multiple coil Bourdon tube type. Well fluid pressure is transmitted through a rubber diaphragm to fluid contained inside the Bourdon tube. Pressure increases cause the tube to uncoil. The rotation is transferred to a stylus which makes a mark, usually on a coated metal chart. The recording chart is moved vertically by a clock with the speed of movement along one axis of the chart dependent upon the clock selected. The rotation of the stylus in one direction by the Bourdon tube records pressures. The movement of the chart by the clock in the other direction records time. The relative motion of each yields a pressure time chart. Electronic gauges using quartz crystal or strain gauge transducers provide high-resolution pressure and temperature measurements. The electronic gauges may be coupled with downhole electronic memories or connected through an electric wire line to surface instruments. The downhole memory recorder can be set to record pressure and temperature on a periodic basis at intervals from 5 seconds to 128 minutes. Upon retrieval, the information stored in the memory is read by surface electronics to provide an immediate digital printout of the data.
It is possible to connect the electronic gauge in the subsurface through an electric wire line, which is run inside the drill pipe, to the surface and then to a recording device.
Using this equipment, real-time test data is available at the surface so that the quality of the test may be observed, and with suitable computer, immediate test calculations may be performed. It is possible then to perform a complete analysis of a well test at the surface, even before the test tools have been moved from the zone being tested. It also means that a test may be continued until sufficient data has been obtained, not too long and not too short.
Selecting the appropriate pressure recording system depends on test objectives. You will find some suggestions in your manual. Now let's say a few words about the surface facilities needed for a test.
The surface equipment that may be required for a DST on an offshore flowing well is shown in this schematic. Production flows up through the surface test tree, then through a safety valve to a data header, where temperature is measured and fluid samples may be taken for laboratory analysis. Production then flows through either the positive or adjustable choke. In some cases, both chokes may be closed and production directed through the manifold bypass. From the manifold, the produced fluids flow to the heat exchanger, where they are heated before being separated. Oil, gas, and water are separated into individual phases in the separator and then individually metered. A test tank may be available to use in cleaning up the well, taking samples, and proving liquid flow meters. After metering, the hydrocarbons are disposed of through a flare or burner, or collected in tanks or pipelines. The water is safely disposed of.
A well may be tested for a number of different reasons during its life. The reasons usually coincide with the need to make decisions with respect to the well or reservoir, or the fact that an opportunity presents itself to add to the database of the well. When we do test a well, though, we must prepare a complete test package.
To be complete, the test package should include the following key elements. A statement of test objectives, including why the well is being tested and what we expect to learn from the test data.
A proposed test design, including the specification of the type of test to be run, flow rates, shut-in periods, durations, and contingency procedures in the event that the test has to be altered in the field.
The mechanical design should specify the required surface and subsurface mechanical system.
The instrumentation package must also be specified. It should include the pressure and temperature measuring and recording devices, as well as the wireline recommendations.
The package should also include specifications for sampling produced fluids, how many samples to take, when, and where.
Finally, a complete well test reporting system must be prepared to be sure that the well test procedures are communicated clearly to all persons concerned with the test, and that all test data is recorded properly and systematically. Let's summarize what we've learned so far.
In this last unit, we have discussed the more practical aspects of well testing, how flow rates are controlled, the surface equipment required during a test, and the options for sensing and recording pressure. Finally, we discussed the key elements of a well test package, from stating the test objectives to communication and reporting.
With a test properly designed and conducted, interpretation of test data may then be undertaken with confidence. You may well ask where you might go next in this series.
We can recommend PE 402 for gas well testing, and PE 403 for more detail and examples on well testing.
PE 404 is devoted to both onshore and offshore drill stem testing and includes a major section on downhole tools.
PE 405 discusses core analysis. And finally, the last module in the series, PE 406, is devoted to reservoir fluids, their sampling and analysis.
Before closing, let me suggest that you work exercises 9 and 10 in your manual, and then move on to the other modules in this series.